Hey, appreciate you guys taking the time to listen. So we're from Fhenix. We're basically working on a private L2, using FHE. So let's just dive right in. Yeah, so real quickly, just from a high level, like Fhenix is the first L2 on ETH to leverage like composable private encrypted states through, I'm sure you're all familiar with FHE. But yeah, the first blockchain is general support. So here's a link to the Discord if you are interested in joining the community. Yeah, and if anyone's interested in working on some sort of development, just real quickly, here's a QR code to the has some things to help you guys set up in terms of development, different documentations. But anyway, we'll dive right in. So kind of what is like this like FHE in general? Again, like won't spend too much time on it, but from a high level, it's basically the ability to run operations on kind of like an encrypted field. So in this sense, you are avoiding the need to decrypt. And so generally this kind of like homomorphism, you can kind of think of it as like what you do to like field A should happen to field B. And in this case, it's kind of like what you do to the plain text in some way should have some direct correlation with what happens to the corresponding ciphertext. And so fully homomorphic encryption is kind of this option to do this over and over again, sort of like in do arbitrary computation. But yeah. So just basically you can kind of, traditionally run a function on like these private inputs exactly, or you would have to like decrypt and run this. But essentially in this case, you can do the encryption locally on the client side and then, send this encrypted function. It is slow, but like at least it's the completely server side. So the server itself actually doesn't get access to the information when it's doing the necessary operation. And so like in some ways like FHE is kind of the new ZK. I mean, not really, but just sort of in the sense that like it's kind of early. It's probably still like in some ways the first time people are kind of getting introduced to FHE, sort of like where the state of like, I guess ZK was kind of in like 2020 in the sense where it's like there's not really like production apps. Still mostly it's kind of like research into like different methods, implementations. But like for a quick, overview of like the history of like these homomorphic encryption in general. As you can see, like, around in like the 1970s, some seminal work came out which kind of like demonstrated the concept of homomorphic encryption for privacy in general. And then, for 30 years, there was like, a lot of progress being made on things like partial homomorphisms, homomorphic encryption, and then 2009, like there's this new concept, sort of like bootstrapping, which is like, if you think about FHE is kind of like noisy encryption in the sense where it's like you need to throw in some noise or some fake stuff with the real stuff in order to obfuscate, what's actually happening. So I guess it's kind of it's sort of similar to. When you're playing poker or something, you got to actually bluff sometimes, or you can't just play things completely straight, or else people are just going to fold every time you go in because, like, obviously you'll have the nuts. So, and then from here, there's a bunch of different branches. Specifically, we are using the TFHE, kind of like this fast bootstrapping branch. Thanks. Versus, which is like created and maintained by Zama. And so we can, not to harp on that too much specifically, but yeah. So kind of just from a high level, like I'm sure a lot of people, in the space, it's, we're more familiar with kind of using approaches kind of centered around like ZK, I guess, for privacy, at least in terms of the narrative to some degree. But there are some limitations here, right, in the sense that like it's difficult to, run these sort of like operations on some sort of like, different parties, multi-party privacy. So in this case, you can kind of see that, like, yes, technically they do both provide privacy, and I'm sure we're familiar with the concept of, like, with the ZK in general, right? You can prove something without having to reveal what you're actually trying to, the contents of it. So in that sense, you have, like, single-use privacy. But, like, if you are trying to construct the proof, and the proof, the inputs of the proof need to be plain text, adversarial plain text, in the sense where it's like person A doesn't want person B to know what person A has, and vice versa for person B. So then that's kind of where you kind of get these issues in terms of, like, composability, because a lot of it, ends up having to be off-chain, and you can use other kind of methods with it, but generally speaking, right, it's more for verification. And so because of this, like, the plain text itself ends up being known if you try to use it for multi-parties. So again, this has specific use cases, right? But, like, certain things, it's kind of difficult if you need to have a certain level of, like, on-chain state privacy, right? So for a lot of projects that will, like, I guess, market themselves sort of as, like, we're trying to do, like, MEV protection or something, and a lot of it maybe comes down to, like, encryption in transit versus, like, the actual state itself becoming encrypted. Because, for example, if you have, like, a pool and you want to keep a running balance of what this pool is, it's going to have a lot of different interactions from a lot of different parties, and so trying to get some sort of, like, cycle verification of each of these parties is going to be kind of a problem within itself. And so here's kind of like a overview of some different privacy technologies that are kind of being used right now, and just going over some specific research examples, deployments that are either live or in testnet, and then kind of like the main features, going over the pros and cons. So not to spend too much time here, but essentially, if you think of something like a trust execution environment, right, it could be fast, programmable. There are known attack vectors, and the physical the physical nature of it makes it applicable for some cases and not as applicable for others. Different types of MPC, like maybe involving something like secret sharing, could have very fast compute. Does have some limitations in terms of, like, the communication requirements. Essentially requiring more interactions versus something like FHE, which is a little bit more, basically you're just doing these operations. You don't necessarily need to do some sort of, like, round for consensus for these operations unless you're maybe doing something like a decryption, but we'll get to that in a little bit. And like I said, like, for ZKPs, right, it's pretty well established for certain use cases, but it's primarily kind of for, like, single-use privacy, again, like, because within itself, I mean, it could be used with you can use to verify other methods, but, like, in a vacuum, it does lack some stuff in terms of, like, the leaking the plain text to the actual prover. So why are FHE rollups specifically? I'm sure a lot of you have worked with like Zama's projects, or maybe some other FHE blockchains that are taking different approaches, such as, like, an L1 approach. There's going to be some constraints when it comes to building something out like an L. Like, generally speaking, obviously there's a lot of, like, nuance to it, but there could be issues in trying to run this FHE, for example, at, like, the consensus layer, the execution layer, versus you get a little bit more options when you go with a more modular approach. But anyways, like, we are working on the first, like, FHE rollup, and it's where users will encrypt their transactions input and send them to the sequencer, and then the ordering the transactions. Is similar in the sense where it's kind of like it's like another like an L2 essentially. Like, in this case, we are using Nitro Prover, and one of the reasons we use that is because it has if you guys are familiar with, like, the Arbitrum stylus, sort of like the WASM execution for the, like, TFHERS operations themselves, and then that talks to the EVM component, and then from there it's able to verify the state of the L2 to the L1, as you can see. So like the standard rules of optimistic verification in general, there is a challenge where you can challenge the state. Ideally, in the future, it would be great to be able to verify, succinctly, so to avoid these periods. But I think it just kind of comes down to general scaling in general, right? Like hopefully there's a lot of progress that's being made on verifiable FHE, but we'll get to that. Yeah, this is just, similar slide, just kind of going over FHEOS, which is just some other aspects that we're working into our network that kind of allows us to interact with different parts of our stack specifically. So earlier, I talked a little bit about like the threshold network, and again, another similar concept to things that are being worked on here. So basically, like like when there is a decryption request that needs to be sent to the network, you can kind of think about that it's sent, needs to be approved basically, and kind of this like, the secret sharing like MPC approach. So it's going to have, it's going to figure out like who or what caller, what contract has access to a specific ciphertext, and like can that ciphertext be crypted? And again, there's a lot of like nuance here. Of course, this opens things up to additional trust assumptions, that can be predefined by the specific decryption protocol. So this has usual MPC assumptions. I'm sure some of you guys are familiar with the concept of threshold decryption, like when you're working with Zama. I believe that Zama is currently moving towards like an asynchronous decryption approach, and I think that was actually just released in a recent version. And I think the old version was sunsetted. Fhenix, we do it slightly different in the sense where we have the DevX actually, instead of having to call the decryption network and wait for like the async response, like I think in the form of callback function, we are actually able to make it so it's similar to how like the decryption used to work before I think the synchronous decryption was sunset in the recent version of the FHE VM. So the DevX is similar to how it kind of used to be, but in practice, like in terms of being able to kind of remove asynchronously execute that decryption call in order to update the state of the actual FHE, like the VM itself. So that's kind of like something that we're working on at Fhenix. So fraud proofs, kind of like I was talking about earlier, like in order to be an L2, right, the proof itself has to be verified in order to verify like the correct state changes, standard L2 stuff. But one of the reasons why is this kind of done in Solidity versus, or like why prefer to do it in Rust, like the operations themselves, kind of like the TFHE library versus just doing it in Solidity. It's just compatibility is going to be an issue, right? Like trying to run all of that. In just pure Solidity would has its own problems. So like I said, we're using the prover, the Nitro stack, which is from Arbitrum. Like again, for those of you who might be familiar with Stylus, but it's basically to run this kind of like WASM interpreter between like the two VMs so that you can consolidate it in the L1 state for the proof. And so, right, this comes in the form of like native FHE precompiles that you can call from your Solidity function, but we'll get there in a second. And again, like this is, obviously it has the same issues as with general optimistic verification for an L2, right, that you're going to have to wait for these arbitration periods, but hopefully they're infrequent. Is kind of the idea. So yeah, touching on like how this is actually imported. So you can import FHE, these FHE operations, these data types, et cetera, directly from, basically one line of code. And from here, this allows you to work as you would pretty similarly with native Solidity. So, if you're already pretty familiar with Solidity, picking up these. Adding FHE to your contracts is relatively straightforward. There are some nuances to it, and we'll get to that in a second. So, at Fhenix, we have a couple options for development. If you want to kind of set up like a local instance, you just have to, we have a guide that has a few steps, but basically it'll allow you to run these FHE operations locally. So for those of you that, prefer to work with hard hat, this is a solid option. And we also have a remix plugin. I think Tom will go over it a little bit more in the demonstration. But basically, if you guys have used Remix before, it's kind of like a browser IDE that you can like generate the ciphertext. Well, there's a plugin that allows you to generate the ciphertext, plug them into as function inputs, do some sort of sealed output in order to actually view what the encrypted contents are going to be, and we'll get to the sealed outputs in a second. I personally am kind of a fan of like the Remix plugin in general, at least just from like the perspective of like it kind of helps, at least for me, right? It kind of helped me like visualize sort of like what was happening when I was first kind of getting into it, right? Like what is the ciphertext? What does it look like? Where am I passing in? How do I view it? How do I go through the process of it? So I definitely think it's a solid tool, and you know, in the future we are working on Foundry integration. So this is something that, you know, our development team is, you know, working on to try to deliver, hopefully in the near future. But yeah, so inputs are slightly different in Fhenix. I mean, I guess even slightly slightly in the sense where like it's different from general EVM stuff. It's also slightly different, I think, from you know, original implementations of FHE in the sense where we have something like an in-EU and 8, which is basically just like, these are kind of just the two options right here that you have to like pass in like an encrypted 8-bit integer in this case, unsigned integer in this case. So basically what you're doing is you can kind of pass in this like arbitrary bytecode or this other slightly different format, but both basically represent the same encrypted integer. And in this case, there's you know, there's a method to essentially convert the passed in EU and 8 or the bytecode in this case, and convert it to like a version of an encrypted integer that can be used with the rest of your contract. And so again, one of the other, in my opinion, this is probably one of the trickiest parts of working with FHE, but it's familiar. It's similar to other things you might have been familiar with in the sense of, you know, it acts sort of like constant time code, where you have a single code path and you need to avoid branching, right? So here's kind of like an example. Like bad is sort of in the sense where like I'm sure we're all familiar, or at least initially started with the simple like if else syntax, where basically you just have a condition for the if and then branch and then else the other branch. So again, this is something that's not really feasible currently with the way that we are building at Fhenix. So something that is a better method that you can be applied in some use cases definitely takes some like thinking, getting used to, because it's sort of like a conditional slot, but you can't have a conditional write, if that makes sense. Like a conditional assignment is possible, conditional write isn't, because it'll write both ways because both branches need to execute, but basically, this is a selector method, which is similar to like the CMUX like multiplexer. But basically, there's just an initial value that gets assigned to either A or B, depending on whether if that first encrypted value is true or false, and it's basically represented here as an e-bool, the e-boolean, which is essentially what it sounds like. Yeah, and so require statements also are slightly different. I think that one of the basically, you know, when you use a require statement in a normal function, in native EVM, basically, right, you want to check something like if this number is greater than so and so, just don't let this happen because it'll lead to a bad state, etc. And so, how is this slightly different in FHE? Well, in FHE, you can basically check to see if an encrypted number meets a certain condition. Like, let's say the certain value of this input needs to be like greater than 5. Or else, like, it just won't execute correctly. So, how do you really do that if you are using FHE? So I think in previous versions of the ZK VM, and again, this could be maybe not super up to date, but my understanding is that previous versions of the ZK VM used to allow you to use like some sort of FHE require. I think currently now that decryption is like kind of changing, sort of like what I said earlier, from like when it used to be synchronous, now it's a call. I'm not sure if you can do that anymore, but at least on Fhenix, I think that you know, the way that we're constructing the DevX for the synchronous and like the whole process of the asynchronous decryption does allow you to have like these quote FHE requires, so you can revert a specific state transition, I guess, if you would, or transaction execution based off of an encrypted comparison. You could basically do that, you know, similarly as if the DevX was, you know, kind of previous synchronous decryption. So that's something that's pretty interesting. And conversion leakage. So, you know, I think a simple way of putting this is sort of like, you if there is a trace of something somewhere, then like there is a history of it. So like if you leaked plain text to memory at some point, then you open yourself up to the vulnerability of like being able to get traced, and boom, that's like a general, I guess, honeypot for vulnerability. And again, that's kind of like the whole essence of FHE, right? Like you want to avoid being able to decrypt. You decrypt, that's basically a major vulnerability. So end-to-end encryption is necessary, or in order to have this like a true, I guess, like end-to-end encryption, you need to be able to run the private operations. And so here's just a really simple example: is if you pass in like an unencrypted unsigned integer, and then you try to convert that to an encrypted unsigned integer. So obviously, people are going to be able, if you look through this, if you trace it up, you can find that the original input was unencrypted, and then from there, right, every subsequent operation that you do from it is going to leak. Someone's going to be able to reverse engineer what you did. So again, I think this is just kind of like a design constraint in general, sort of like. You have to really be cognizant of the fact that you're not passing in or using an unencrypted integer and assuming that it's going to be encrypted because you're using it later, right? Because the state is visible. So what is Fhenix.js? Fhenix.js is, maybe some of you guys might be familiar with like, I think it's like FHE I believe. But it's essentially sort of like the ability to, assign a specific data type to a number. So like, as you saw in some of these earlier functions, some of them have inputs that require you to actually pass in a ciphertext, right? But how are you generating the ciphertext on the front end for your applications or for testing in general? So basically here's like, let's say you want a EU in 8 and you want that EU in plain text value to be 5. So you can use that number for whatever, I guess, you need to use it for. So in this case, this basically allows you to handle the type creation, and from there, it's relatively similar to, if you guys have worked with like Ethers.js, using that as like, for building your applications, and basically just ABI interactions are going to be similar, just in the sense of like, instead of passing in like the number 5, now you're just passing in this ciphertext that represents the number 5 in the form of this bytecode, and also it allows you to handle permissions. But what are permissions? So permissions are basically kind of like, you have an encrypted field, for example, like, and you only want people to be able to decrypt it or be able to view. Sorry, you only want people to be able to view what this encrypted field is. Maybe you need it for your application. Maybe you need it for whatever, or maybe it's your data and you actually want to be able to see what you put in or how it's changed based on who knows what. So basically, this is like kind of the format of what you can do, how you can handle like conditional permissions, etc. But you kind of think of it in this case where it's sort of like a modifier in Solidity, essentially, where you're kind of requiring that the message.sender has the correct like public key permission, if you would, to view this. So under the hood, it's sort of like the values kind of being decrypted and re-encrypted. So it's similar to the re-encrypt, I believe, in the FHE VM, but it essentially acts relatively similar. And so if you want to add some sort of specific conditions here, this is kind of where you would place it. So it's kind of like, I want to be able to view my token balance, but I don't want anyone else to view my token balance except for like someone who owns my NFT or contributed to something. But basically, this is how these permissions can be assigned. And so just from a high level, here's just kind of what a simple smart contract is going to, or like a smart contract built on Fhenix is going to look like. As you can see, it's relatively similar to something that, you're familiar, if you're a Solidity dev, you're probably already familiar with, right? There's just some changes here. I think it's kind of nice in the sense where you're not required to like learn a new language or like a DSL or like a whole new process, figure out, like download all this stuff for. I think specifically, in my opinion, like if you're working on something that's specifically privacy focused and you're a Solidity dev or you want to work with Solidity ecosystem, like generally speaking, I think the DevX here is pretty nice, and a lot of this is similar to stuff that's being built on Zama, so a lot of credit there. It's and if anyone is planning to participate at the ETH Global hackathon this weekend, we have a 5K bounty. So if you're interested, ideally we are looking for like full stack applications in general, but the requirements can be pretty flexible if you have a cool idea you want to work on. And again, if you're interested, like feel free to message me. So, and again, just from a high level, like there are going to be, I'm sure we're all familiar with the concept that like FHE is expensive, right? Like it's tough, it's slow, it's whatever. Like, There are some nuances here, just to, I guess, remain cognizant of that. You know, certain things are going to take longer, and some of the primary factors are going to be like, what operation are you doing specifically, right? Like, for example, adding two numbers is probably going to be easier than dividing two numbers, for example. And also the size of the numbers that you're trying to play with or operate on is going to come into effect here. But yeah, and here's some tips from some of our developers. Is that, you know, surprisingly, I believe that, you know, using things like ChatGPT are pretty, you know, pretty solid for creating like the structure of some of your stuff. So definitely of your functions, et cetera, or just your contract, your code in general. So that's definitely good here. I think, you know, this is just an example of how you could use a generate a vote function. And I'll hand this off to Tom to go over more in depth of how voting will work. But yeah, I mean, thank you for listening. This is just
All right. Thanks, Kyle. Okay, so I'll zoom in a minute, but first of all, thanks again for coming and listening. What we're going to do now is we're going to dive in a little bit and look at a bit more technical. I guess my main goal here is to kind of present sort of a little of a different approach on how to write FHE code or you know, Kyle touched on it a little bit, where it sort of looks like maybe constant time code or stuff like that, and we'll see like different consideration we need to have when writing something like this. So let me zoom in a little bit. Oops, sorry. So just out of curiosity, how many developers are in here on the raise of hands? Okay, Peter, I know you. All right, so we're gonna go over confidential voting contract. That's our goal. And basically, what we want to achieve here is to have confidential votes, right? We don't want other people to see what every person in a DAO or something like this votes on, because we want more transparent, more authentic vote results. So let's go over real quick on the constructor. We're basically receiving a proposal. We have an array of options, which is going to be like, let's say for now it's going to be like 0, 1, 2, 3. Like let's say we have 4 options. So a people that is voting is just sending the code for the option he wants to vote for. And we have a voting period. Nothing too special here. If you look at the state part of the contract, you can see that already here, and it's similar to like the code samples that Kyle demonstrated, where usually you would have, for example, we have an option and a tally where you want to count votes, and you usually have just regular uints. Now you have encrypted uints, you have euints, and these state variables are obviously encrypted. So let's look at the voting function, for example, which is going to be an interesting function to look at. So first of all, we're making all sorts of sanity checks that the voting is still running, etc. Then, just as we saw in the presentation, we receive basically the vote. So we accept an EUINT 8, which is the specific option that the user is voting for, and then we're converting it to an EUINT 8. So we're receiving bytes. We need to convert them to the actual data type. We're doing some sort of validity checks, and then we're storing the vote that the actual user voted for, and then we're calling the add to tally function. Now, if we go to the add to tally function, what we see here is pretty interesting because, again, we need to think of this as sort of a constant time code because how does it look like on the state? We have basically, let's say, 4 options for this specific vote. We have option 0, option 1, option 2, option 3. And for each of these options, if, for example, they were plain text, even if my vote would be encrypted, and then like an outside looker would be able to see that after my vote, the tally for option 1 increased by 1. Obviously, everyone knows what I voted for, right? So I have to keep these numbers encrypted as well, obviously. Now, I have a state variable for every option, and each of them contains an encrypted number. But then again, for an outside looker, if we are going to analyze what's actually happening on chain, if I am voting again for option 1, and then an outside user looks at the values and see, okay, I don't know what these values represents because it's just an encrypted blob, but only the value for option 1 changed because I increased it by 1. Still an outside looker it would be obvious what I voted for, right? So what we actually want to do here, and this is kind of fun. Like I like to write challenging code and think you have to kind of think a bit outside of the box. But here the solution is pretty simple. You want to add 1, like increment the tally of the option I voted for by 1, and then increment every other option by 0. And that's like exactly the result you want to end up with. So what we're doing here is we're basically running over every option in a for loop. So every time I vote, like every time a user votes, and say there are 4 options, we do every time 4 loops in this for loop, like the number 4 loops in this loop. And every time I'm checking if the option I received is equal to the specific option I'm comparing to right now. And then I will get an equal result of 0 or 1. 0 being false, 1 being true. And then I can just add this result, which will be 0 or 1, and I can add it to the respective field that actually tallying the results. So again, every time user votes, we need to add 0 to every option other than the option the user actually voted for, which is 1. And then an outside looker can't actually tell what's going on behind the scenes. So that's something interesting to look at. Something else that I wanted to show you guys. Let's see. Okay, so let's see on another example of the permissions mechanism, where you, just as Kyle showed, you add a permission, you add a modifier, and you basically what you do is the user uses his private key to sign a message that actually authenticates him. So that's what we receive in the signature here, and we can use the seal output function. Sorry. What the seal output function does is it basically decrypts the result from using the original private key of the network. But then we also want to send the user the result in a protected way. So we want to encrypt the result using the user's key in order for him to be able to open it and decipher it later. So that's basically what seal output does. It decrypts it using the network key, which the user doesn't hold, obviously, and then re-encrypts it with his own key. That's what we're doing here. And finally, when the result is over, we're calling the finalize function, when again we have a bunch of validity checks and all that. And then we again basically need to go over, because remember, this is still encrypted. And we might want to encrypt it by this part, and we might not. So here we need to go again over every tally of every option. We need to decrypt it and basically select the the largest, or the winning one, the largest, the option that got the most votes, basically. So this is a good use case for select, or if you're familiar with FHE VM, that would be CMOX, where basically you're checking if the current winning tally that we looked for is greater than, or sorry, the new tally is greater than the current winning tally. If it is, you return the current option you're checking, and if not, you're staying with the same winning option. And then by the end of this function, we're ending up with a winning option and a winning tally. Yeah, so this is basically an example of very simple voting, very simple, very naive voting contract. We have this example and many others in our docs, by the way. Any questions about this code or about the slides earlier? All right, we'll be hanging out here in the next few minutes, so you can just tap us on the shoulder and ask if you have anything. And also, by the way, we have an event tomorrow called Encryption Day. So if you're interested in hearing, a bunch of interesting talks and stuff, so you're all invited. You can also sign up, or if you don't know how, just talk to us. Yeah, thank you very much.